Right. Yeah, I would like to thank my boss here who said that I couldn't do this on account of it being too silly. I'm just going to move that up because we're all about the safety. Yep. I'm wearing actually the safety wear.
That better?
Yeah. So, yeah, after Mike said that
Speak into it.
No, I'm loud. I'm used to talking in lecture theatres. So yeah, after I was told that I could not teach quantum physics to primary school children through interpretive dance by my boss here, because it was silly, I was actually commissioned to do this piece. So thanks to Mike and also thanks to Nick Reinberger of ABC Radio who commissioned this piece, and to Max. Yeah. You'll find out later. Okay, so I've come to you to talk about quantum physics. And as we know, throughout history, humans have speculated about the nature of light and matter. And we gradually came to understand matter as being made out of particles. We call these atoms. We found out that they're made out of smaller particles called protons, neutrons, and electrons. More about electrons later. Light was more of a puzzle. But by the end of the 19th century, we solved that puzzle. Light is a wave. Not a wave like waves on water or sound waves, so waving electric and magnetic fields. And it followed the laws that govern other waves. But then, at the dawn of the 20th century, came the age of quantum physics, where stranger rules apply.
Yeah.
So what do we mean by quantum? Well, in classical physics, all of our physical quantities like mass, momentum, velocity, energy, they can take any value. And when they move between values, no numbers get skipped.
So we.
Yeah, that's certainly. But electromagnetic energy can't take just any value. Electromagnetic energy comes in little packets if we look closely enough, or quanta, that we call photons. And we can't break electromagnetic energy, we can't break photons down into smaller values. Particles have mass, they have momentum, and they have a definite position in space. And when a particle moves from A to B, it has to travel through all the space in between in order. Waves, on the other hand, well, waves have energy too, like particles, but waves don't have mass. They don't have a position in space. They're spread out in space and spread out in time. And waves can do something that particles never do. If two waves meet at the same point in space, they travel right through each other. Momentarily they add together, and then they pass on their way, completely unchanged. In the quantum world, waves can behave like particles, and particles can behave like waves. This is what we call wave-particle duality. So for example, electrons, remember electrons? They're particles. Well, they can behave, electrons in atoms can behave like waves on a guitar string. Their wavelengths and their energies are quantized. They're only allowed to be certain values that will fit into the space, and all the values in between are forbidden. So when electrons in atoms change their energies, they have to jump across these forbidden gaps, taking in or giving out just the right amount of energy. What kind of energy? Electromagnetic energy. Light. So, is light really a particle? And are particles really waves? Are electrons orbiting around atoms like those little diagrams that we see? Or is something stranger going on? Well, Niels Bohr said that when it comes to, and incidentally, I don't care how you pronounce his name, Niels Bohr said...
How do you say De Bruyne?
De broccoli. Niels Bohr said that when it comes to atoms, language can be used only as in poetry. Niels Bohr, in honor of wave-particle duality, took the Tai Chi symbol, the symbol we know as the yin-yang, as his coat of arms. And at CERN in Geneva, home of the Large Hadron Collider and decades of particle physics research, there stands a statue of Shiva Nataraja, Lord of the Dance, reminding us of the endless subatomic dance of waves, particles, energy, matter, creation, and destruction.